Welcome to On the Metal, Tales from the Hardware Software Interface. I'm Bryan Cantrill. With me, as always, is Jess Frazelle. Hey, Jess.
Hey, Bryan.
And joining us is our boss, Steve Tuck. Hey, Steve.
Lucky to be here.
All right, keep us in line. Jess, you wanna tell us who's joined us in the garage today?
Yes, today we have Jeff Rothschild. Very fortunate to have him, and we have brought him into the garage, and we actually already started talking about some stuff that we have in here. One of which was an IBM BASIC manual.
And Jeff, when you came, first of all, welcome to On the Metal. It's great to have you.
Thank you.
And you immediately started looking at our manuals. And I know that a lot of them have personal resonance for me and personal resonance for you. And I know you saw the IBM manuals. And those were great manuals, weren't they? The boxes.
They were. It was felt very impressive to have that whole row of boxes sitting on your desk next to the IBM PC. It felt quite official.
All right. So tell us when you first had those manuals, and tell us about some of those manuals that meant something to you.
Well, I bought a IBM PC right when it came out. I just figured this was going to be an important platform, and I should know everything there was to know about it. I figured if I knew a little bit more than somebody else, there might be some advantage to that. First thing I did was I noticed there was a disassembler. And so I disassembled MS-DOS. I laid out 20 feet of paper listing on the floor of my apartment and got to work commenting it.
Wow, that must have been so. All right, so your apartment. So you're an adult at this point. So
sort of, yeah.
You know, right, exactly. Right.
I was in my 20s.
You're in your 20s. So perfect timing for the PC. And what did you learn from MS-DOS? That must have been an incredible educational experience.
Well, I understood how the file control blocks worked. I recognized that there was state associated with an open file that persisted past the close of the file. And oddly enough, I did find that very useful later because some applications would operate on a file, would officially do a close, and then continue to move the file pointer and do reads and writes because it didn't matter. That state was not eliminated on close. So the FCB-based I/O was, you had to understand it. I needed to understand stack switching, moving between the user stack and the system stack. So it was quite useful to have that commented code.
Wow. And did you do that solo? Did you?
On my own.
Wow. And it's disassembly, obviously. So it does not come with even, do you have symbols? Do you have identifiers? What did you have to go on?
No, I just created my own. There was numeric identifiers in the disassembly, but then I created my own symbols. Once I figured out what something did, I'd create a name for it. Oddly enough, many years later, I did see portions of MS-DOS and had to go back and check. And my names weren't that different in most cases. You don't still have that no, of course
copy?
Not.
It would be invaluable, I think, to actually learn how it worked.
That's so cool.
And I also used it in order to do an I/O redirector. One of the first products I did on MS-DOS was a file redirector for moving data to moving file ops to a UNIX system. So effectively like a primitive version of NFS. But there was no VFS interface in MS-DOS. So I created something like that in order to do a product called PC Interface that allowed a MS-DOS program to use a Unix host as its remote file system.
What year is that?
Oh, early 80s.
Wow.
That technology was purchased by Sun Microsystems and became the client side of PC NFS.
Whoa.
Wow.
Because the protocol was close enough to what eventually Sun did as NFS.
Do you ever wonder if that software is still running anywhere today?
Oh, I'm sure it is. I'm sure in some government agency, there's a machine somebody hasn't touched in 30 years. It's not on the internet, so nobody needs to update it. And, I suspect it's still running somewhere.
That is amazing. And is this, this isn't in the day, this is all real mode, correct?
Oh, yeah. Yes.
So this is all effectively 16-bit disassembly.
That's correct.
Not a lot of registers to work with.
No. And, had to do this in, a few number of bytes. Most machines at that time were sold with 64K bytes of RAM. So you couldn't waste anything. So I did a simple IP UDP implementation, all in assembler in about 2.5K.
Whoa.
So
that thing would fly today.
No TCP. That would have been, I couldn't have done that in that.
TCP would have been tough.
That would have been harder.
With those constraints.
Simple IP UDP and, ARP and reverse ARP, all in about 2.5K.
That's amazing. And what kind of machine were you talking to?
This was a
3B2?
3B2, exactly.
It
was the AT&T 3B2.
A machine that, if memory serves correctly, stacks grew up on the 3B2. Is that right?
That's lost for time. I don't remember.
The only reason I say that is because I ripped out some code that we historically allowed stacks to grow up or down. And I determined that the only reason that upward stack growth was there was for the 3B2 back in the day.
I can believe that.
Right.
It was a fun machine. It was very Unix and C centric. That detail I'm luckily have forgotten.
That's right.
So was that machine the favorite machine that you ever owned, or did you have another one?
Oh, machines I've owned. I can't say that the machines I've owned I've ever had a favorite. I enjoyed working on a Xerox Sigma 7 when I was in school, which is a great computer, impressive for what you could do with it, with of course, very little basic hardware performance.
Wow. So what was the Sigma 7 based on?
Sigma 7 was the Scientific Data Systems was the company that developed the architecture. They sold that to Xerox. It was a 32-bit machine.
A 32-bit machine. That is very early for 32 bits. That's like having
is an early 32-bit machine, early 70s development. Had, I think, about probably a megabyte of memory. It used a fixed head disk, what they called a drum, and could support 40, 50 terminal users. So people were limited by the speed of the input device. So you're typing on a Teletype 110. So nothing was very fast. It was the university shared resource.
That's amazing. You think that machine had a megabyte of RAM, and then a decade later, you're buying a machine with 64K of RAM. I mean, it just shows you how dichotomous computing was in terms of the computers that you would use versus the computers you could buy.
Of course.
It's amazing.
It's almost interesting, then how people kind of just consume resources without even thinking about them today.
Well, that's a commonly held attitude, I think, that we view. I mean, how, especially growing up in that era, you must view us as being just profligate users of everything today.
Of course, terribly wasteful. But it's sort of a lost skill, and maybe it should be lost. I mean, we used to. I remember when people would grade papers when I was in school. If somebody could show that you could eliminate 20 bytes, well, you lost half a grade. I mean, because every byte mattered, and today it doesn't.
I feel like there's still pockets where every byte matters.
Of course, when you're dealing with obviously large amounts of data, then the representation of each individual data element, clearly every byte matters. But when you're writing a piece of functional code, it's more, I'd say, readability and your ability to maintain and enhance that code is more important as to whether you achieve the utmost compact representation.
And so was the Sigma 7, was that your first real big machine that you used?
It was, yes. I then moved from there to the PDP-10.
Ooh, I have a PDP-11 replica inside and then a PDP-8, but not a 10.
Well, I used the 8 as well. In fact, I worked on the 8 in paper tape.
That's cool.
And that was also an interesting challenge to do your development of paper tape. And the PDP-10, a 36-bit machine, and it was an interesting beast. I actually used to have fun coding the PDP-10 not using the assembler because for some reason that I can't explain, it may have been, in fact, it may be indicative of a social defect, but I thought it was fun to learn the machine language and code without the assembler. So I just open up an octal editor and could write some fairly simple programs.
That's cool.
A useless trick. And again, if I saw someone doing that today, I would be worried.
I was just going to ask, is everything done with an assembler today? Is it unheard of that you would not use an assembler?
Certainly when Jeff was saying, I didn't use the assembler, I was saying, wow, you're using a higher level language but no, it's like he was actually going lower. So the assembler takes the actual instructions to the CPU and encodes them in the binary representation. What Jeff was manipulating was actually the binary representation, albeit.
Well, I wrote it in octal.
Right,
yes.
Right, exactly. Yeah, I'm not a primate here. I mean, obviously I would work in octal, not binary.
That's cool.
That's amazing. And so you must have had the opcode. I mean, you probably still know some of those opcodes.
No, I don't. I luckily have forgotten that. I mean, there's a finite amount I think you can store, and that register has been cleared and reused many times.
Thank God, right? It's been so. All right, so you were on the PDP, and how many years did you work on the PDP?
Oh, just while I was in school for 2-3 years.
And where did you head to after school?
Oh, I went to work at Honeywell. I spent a year at Honeywell's Large Information Systems division. And this was the old General Electric computer company. Their system was a 36-bit machine as well, a real memory system at the point that I joined, though they were working on trying to add a virtual memory capability. Interesting machine. It had 6-bit bytes, 8-bit bytes, and 9-bit bytes. So you could choose how many characters to pack into a word. And of course, it meant that, each piece of software had to identify its conventions for byte encoding, which wasn't that unusual in the day. We had both ASCII and EBCIDIC in use at the same time.
Right. EBCIDIC is probably worth explaining. I know, Steve, there's no way you know EBCIDIC.
Of course.
I hope not.
No, I have no idea. What's EBCIDIC?
It's a character encoding that IBM was using through, I guess, the 50s and 60s.
It is decimal encoded as binary.
Whoa.
Yeah, and it doesn't make a whole lot of sense. But we still have it lives on today because the x86 still has instructions for binary encoded decimal. It's kind of crazy.
Oh, very good.
ASCII add before multiply, my favorite x86 instruction. So, and for the 9-bit words, what was that? The 9-bit bytes, excuse me. What was that to allow? Why was that a parity bit?
Well, if they fit evenly into 36, so you get 4 characters in the
right.
in the word. 8 didn't go in as quite as nicely. So, but the 6-bit, of course, it would fit in the 36-bit.
And so what Honeywell machine is this at this point?
This was, I don't remember the model numbers. It was a Honeywell mainframe, ran the GECOS operating system, implemented in 7400 LS logic.
7400 LS?
Yes.
What does that denote?
That's if you remember the Texas Instruments TTL data book, the yellow sort of yellowish binder that in fact, you don't have one on your shelf here. So
I don't have one on my shelf. No, I've got intense manual in me right now.
That's one you need to buy. And these were a series of small scale and medium scale integration components, and most machines in the 70s were built out of this logic family. So you had 7400, 7400S, which was faster implementation, Schottky implementation, and then the low power Schottky.
I'm embarrassed to say I didn't know Honeywell was ever in the computer business.
Well,
because I think of Honeywell as, thermostats and particularly the family business being in heating and air conditioning, ascribe them to that. But they were a computer company.
They were definitely a computer company, and they were the H in the bunch. So at one point, the computer industry was IBM in the bunch, Burroughs, UNIVAC, NCR, Control Data, and Honeywell.
That's correct.
Got
like
it.
FANG today.
The FANG today, yes.
Okay.
Yes, that's exactly right. 1970s FANG is the bunch.
That's cool.
And of course, all of those companies are more or less out of the computer business. But so Honeywell, and actually Honeywell, although this would probably predate you, the H200, I imagine, would predate you at Honeywell. They made an IBM 1401 clone called the H200, which was transistorized and forced IBM to really get off. IBM was very slow on a transistorized 1401.
That's a machine I wasn't familiar with. I stayed at Honeywell a little less than a year, and it was interesting. They'd given me a relocation bonus when I left school, and once I understood the state of the company and where this organization was going to be going, I just had to calculate how much money could I save and how was my relocation bonus being amortized, because each month I owed them a little bit less. And when the two lines crossed, I left.
You left. So
Yes.
you decided pretty quickly you did not want to work at Honeywell.
The year I was there, they were building a current mode logic version of their architecture, so CML. At the time, ECL was a more broadly accepted technology, higher performance than 7400 LS. However, this was to be their first microcoded machine.
Oh, interesting.
So the CML implementation was very expensive for them. They had their own foundry. They're building their own chips. The The microarchitecture was 10 times faster than the previously directly implemented logic. Unfortunately, you had about 10 micro instructions in each target instruction loop. So the effect was a machine that cost an order of magnitude more.
Interesting.
And delivered exactly the same performance.
Interesting. So you maybe worth explaining microcode, because I feel microcode is something that we don't really have an analog of that today. I know I'm looking at Steve, who I'm sure.
Yeah, I can come up with a couple, but I'd like him to answer.
Microcode is simply you have a low-level interpreter that is interpreting the target instruction set of the machine, and that was a very common implementation technique.
And so it's probably still used underneath. I mean, it is used underneath, under the hood. For x86 obviously has its own microcode underneath. Of course. But you can't write that microcode today.
That's correct, and you couldn't then either.
Interesting.
But the implementers of this system architecture were implementing the target instruction set in micro instructions, about 10 instructions per target instruction. So it all netted out to approximately the same performance.
The same performance. Interesting. And you were actually writing microcode at that point, or
no? I was on a architecture team that really didn't do much of anything. I was just simply calculating when my two lines would cross.
There you go.
My savings and my debt crossed, and I was off to Intel.
Oh, Intel was the next stop.
Yes, it was.
That's dope. So what did you work on at Intel?
Intel used to be a large producer of memory, and they produced DRAM. Not all the DRAM was good. Every process has some waste. Intel was producing a disk emulator for IBM mainframes called the 3805. And it had a very interesting memory controller that could deal with chips that were partially correct and mask that. So it was a great place to pack in memory, possibly memory that you weren't able to sell at retail, and then deliver a solid state disk, something that sat on an IBM channel and provided presumably better performance. What was interesting was that it didn't. It was actually significantly slower than the fixed head disk. And I interviewed at Intel, and and they told me about this project, and they said that they had, a serious issue. They had a backlog of $250 million for these systems, and every one they'd shipped had been returned for being slower than the physical disk that the solid state device was emulating.
That's bad.
Yeah, that's not
so
good.
bad.
Yeah, and it didn't make any sense to me. So being, somewhat cocky, 22-year-old, I said, I could fix that.
Right.
I mean, I knew it was, just maybe there was sloppy code. I didn't know. But I very confidently said I could deal with that. I went back to finish my 2 weeks at Honeywell, and I looked in in a industry rag called Computer World, which is still around, but was very popular in the late 70s. And I saw an interview with the head of this group, the fellow I just interviewed with. And in there, he said, well, yes, it's true. We have this backlog, but we have a solution in hand, and we're going to be shipping it in a month. So I said, well, maybe they don't need me. I called him up and I said, I just read this. Exactly. I was the solution. I said, are you sure you need me? It sounds like you've solved this.
I definitely need you. You are the solution. Wow.
Heard it a PR crisis.
And I hadn't really drank a lot before then, but for the next 2 weeks, I needed a little bit of help getting to sleep at night.
I can imagine.
I wasn't sure that I really could follow through.
You renegotiated your offer.
And what happened? What did you find?
I showed up and looked at this machine, scratched my head for a bit, and stayed up all night with it for probably 2 or 3 weeks with a logic analyzer, trying to find out why this, simple 8086, instruction path was slower than than this physical disk that should be easy to beat. Turned out it was one instruction. It was a repeat move string byte that was used to reinitialize a condition code table for the channel control program. And they didn't catch the one instruction. That was adding sufficient extra time that it made it slower than the fixed head disk. There were two factors in play there. One, their control path was slower. But the other was they didn't understand how the operating systems used a fixed head disk. They figured they knew what the rotational latency was. They knew the switching time is close to 0. So they assumed that the average performance would be approximately half the rotational latency. But of course, IBM has had many years to perfect this technology, and the OSs sorted the sector. So the control program would organize the requests so that it would be doing, position 1, position 2, position 3. So assuming, let's say there were 3 tracks, 3 block positions on a single track, they would always go, let's say modulo 3 and order them 012, 012. And then the other operating systems, they had one time-sharing system that used a little bit different strategy, but also was able to effectively get the rotational latency to close to 0. They put in some spacer records that handled the head switching time and the time for the control program, so that the effective rotational latency was 0. And the folks at Intel, who are great in microcontrollers and in process technology, that wasn't their specialty. They didn't know what operating system designers at IBM had cooked up. So they set their target too low. The product was simply released before they'd achieved what was a useful performance metric for their customer.
Wow. That is insane.
Leading to $250 million.
There's so
backlog.
much in there that's mind-blowing. We're going to have to go back and unpack that a little bit. So first of all, it's a solid state disk. This is, what we now call an SSD, but this is long before solid state disks were.
This is 1979.
And so but it was still volatile, I assume.
Yes. It had a motor generator. So the wall power was plugging a rotating generator or a motor that was running a generator and provided generated power to the memory. So that was to avoid potential corruption from glitches in wall power.
That's cool.
So this thing was loud.
Oh, yeah. This was data center equipment. You weren't supposed to care.
And then on an actual power failure, did it have any way of getting that out to non-volatile storage?
Well, the assumption was the environment it would be had battery backup. But this would carry it through those transitions.
Wow. Interesting. What was the capacity of this thing?
That I can't tell you. This is, again, that register was filled and reused many years ago.
No problem. No, it's just so amazing. And then I latched on to the same thing you latched on to, Steve, about the backlog. $250 million in backlog.
One instruction set led to $250 million of backlog.
Well, they eventually delivered against that backlog. So, they were held up for a number of months while trying to understand this performance issue. And again, it was two-sided. One is they had set the release criteria too high. So they were thinking, 3-4 milliseconds was going to be fine, when in fact they needed to be, a fraction of a millisecond due to the strategies that the OS was using in scheduling I/O. And then they were also too slow, simply due to repeat move string byte.
Right. And so Steve, for context, it may help to know that this is a single instruction that can do a lot of work.
In this case, 256 bytes at a time, where it could have been 128 words. This was a 16-bit machine. That would have already sped it up. But the truth was only a half a dozen entries in that table would typically need to be reset following a single I/O request. So the way the table was used was, given the instructions that were in the channel program, there were only certain instructions that were legal for the next instruction. And then following that instruction, there were other instructions that were legal. So this was determining whether the opcodes that were used in the IBM channel program were legal at that point in the program. At the end of the I/O request, you would have to reset that back to an initial state. Clearly, you could track what changes had taken place and then reset those half a dozen invalid operations at the end of the request.
That's interesting.
Is there an analog to something that you've seen or that we've seen recently that would map to that kind of low level single instruction set that had so far reaching implications?
Single instruction, just to be clear.
Yeah, single instruction.
Yeah, not even instruction set, but it's a single instruction that was I mean, a single instruction can still do a lot of damage today, I think.
It can, but this was somewhat unique. We were dealing with slower memory systems, so anything that moved 256 bytes of memory had a pretty significant delay. For someone reading assembler code, an instruction looks like every other instruction. They seem fairly equivalent. You don't recognize that there is a 2 order of magnitude potential disparity between one instruction and the next one that followed it in the listing. And I think that's what threw the team that was working on this.
So you had a pretty successful first 2 weeks of work.
No, it was a lot of fun. I have to admit, I was like 2 or 3 in the morning, and I'm staring at a logic analyzer, and I'm tracking it down, and suddenly I get to that page in the listing, and there's the repeat move string byte, and I smiled.
Oh, that must have been glorious.
Smiled.
You smiled. Yeah, exactly.
Yeah, I was pretty,
Howl.
I was pretty excited. It took about 15 minutes to code up, the alternate implementation, and I got to sleep that night without a little bit of cognac.
That is amazing. And I can, if you did not emit a howl, I'm impressed with your self-control. I've been known to howl over much smaller finds. So 2 bits of interesting context there. One, so channel programs are something, I mean, Jess, you probably don't know what a channel program is. Yeah. So this is the way, I mean, you want to explain what a channel program is, Jeff?
Well, the I/O is performed by a second computer that had an interface to the mainframe and executed simple programs for doing I/O. And they could deal with tape operations and could, knew the intricacies of tape, but you didn't program the I/O controllers directly from the main instruction set. You'd create a program and deliver that to the channel controller.
And this is something that's coming back a little bit. I mean, not channel programs per se, but the idea of having compute spread away and kind of pushing compute elsewhere to actually. So when you look at like all the offload that we do, right, on the NICs, for example, smart NICs are kind of a modern channel program, albeit in a different form. The other thing that's interesting is the CISC versus RISC. So if you've the complete instruction set versus a reduced instruction set. And so what Jeff found was a single instruction doing a lot of work. And this is predated RISC. Obviously, RISC it wouldn't happen for another couple of years, right?
That's true. But what we did at that point, because removing that instruction certainly moved the product forward and they were able to start making deliveries, it still could have been faster and wasn't meeting full potential of the architecture. So we re-implemented the control program using the AMD 2900 series logic family. So we created a bit slice processor, and we're able to achieve much better performance than we could with an 8086.
And the AMD 29K is an early RISC. I mean, that is a RISC instruction set.
Well, this was the 2900 series.
Not the 29K, okay.
Yes, and so this was a bit slice model where you could really define, you had a opcode controller, but then you could choose the register sets separately, and you could almost design your own instruction set out of the 2900 series.
That was an amazing architecture. I would like to point out there's an AMD 29K manual about 8 inches behind you. Exactly. Well, listen, I'm just very. This is
maybe I hope I'm remembering it correctly. No, it was 2900 versus 29K.
I never programmed it.
Maybe it's the same logic family. So.
Well, but my read on it was always viewed as this real great step forward in CPU design that never really caught on. Is that a fair read?
There were actually quite a few target machines that were implemented in the AMD family. So they used the bit slice processor for the micro instructions and then implement the target instruction with that logic family. It was an interesting architecture. My role in the project, I wrote the assembler that the others on the team used in order to write instructions for this 2900 family instruction set. And that was a fun process. Because I knew who my target audience of developers were. So I would put I wouldn't call them Easter eggs. I would put targeted error messages in that scolded the developers based on my knowledge of their habits.
Do you remember any examples of a particular developer that was scolded in this way?
Oh, one fellow, I don't remember what his habit was, but I knew he would eventually do it. And I just addressed him by name and, said, to err as human, but you're a programmer, something to that effect.
That's good.
That is great.
People were working on what's called an Intel development system. These were single user workstations, so your machine is not network connected. So to have the tool that you've been using for a month or two suddenly address you by name is a particularly unnerving experience. Yes. in a network connected computer, your first thought is I've been hacked.
Right.
And but this is a workstation sitting on your desk connected to nothing.
That is beautiful.
That is amazing. That has given me ideas.
I was gonna say
that is amazing. I know. I love the custom error messages, but you got to think way in advance. That's very impressive. You knew the error messages the errors that people were going to hit. We're going to take a quick break, and then we will be back with more Jeff Rothschild.
On the Metal is brought to you by the Oxide Computer Company.
Wait, did you say computer company, Jess?
Yes, indeed.
But wait a minute, everyone runs on the public cloud. Jeff Bezos owns and operates every computer on the planet. Why would anyone start a computer company?
That is so not true. I have spent a bunch of time talking to folks who are still running on premises, and actually, the consensus among all of them is just a feeling of neglect because everyone thinks that everything is moving to the public cloud, but it's not.
If you're still running on premises, it's because you haven't heard of the cloud, right?
No, there are really good reasons for running on premises still. For security, for latency, strategic reasons for your business.
Wow, the people running on premises must feel like everyone has ignored them.
They do, indeed. So if this is you, please head on over to our website, oxide.computer, sign up for our mailing list, and we would love to get in touch and hear your stories.
We acknowledge that you exist and you've got some really hard technical problems that we're solving. Oxide.computer, come join us. All right, welcome back. We are all sitting slack-jawed listening to some terrific stories of the hardware-software interface from Jeff Rothschild. So, Jeff, you're talking about customizing error messages in the assembler that you.
Well, the fun thing with the assembler was that we were trying to squeeze every cycle out of the machine. So the only piece of novel technology that I had in there was that I could look forward in the assembly program and see, for example, when a condition code would get used. And I might see that it was used in the next instruction. So I would increase the time for the current instruction to allow that condition code to settle through the ALU and then be settled in the condition code. Where if the result of a arithmetic operation was 2 or 3 instructions later, then I could start the next instruction without any additional delay. So it was sort of pipeline optimized.
Yeah, it really was. That's amazing. And
so that was fun to do.
So what would happen if your assembler didn't make that optimization? What would happen?
You would have had to have default. Well, if you set everything too short, then you would have a test, and the test may give the wrong result because the condition code hadn't propagated through the ALU.
Wow. So the assembler is actually load-bearing here. The assembler is responsible for correctness.
That's correct. The assembler, and of course, in modern processors, this type of instruction scheduling and variable delays are all done by the micro instruction set. But this was done in the assembler.
Wow, that is scary. Do you think your assembler had any bugs in it that were found the hard way?
I've never written anything that didn't have bugs in it, so the odds are yes.
But debugging that must have been a challenge.
Well, clearly you could start by putting in very conservative values, and then you'd always have a test version. So you could make the worst case assumption and then determine whether your optimizations had introduced a problem.
And so you're at Intel at this time?
This is at Intel, working on AMD.
Yeah,
using an AMD.
Okay. I just wanted to check myself. I don't know if anyone else had the same
I didn't even put the 2 and 2 together until I was like, wow, that's weird.
In fact, our whole team had to go to AMD headquarters, which was just down the street, and take a training course on the AMD bit slice architecture. And in the AMD training, they asked everyone to say who they worked for. And of course, it was all various companies building control processors. And they got to the Intel group, and it was one person from Intel, second person from Intel, third from Intel. And I think the last member of the group said, so-and-so from Intel Corporate Espionage.
Put it right out there.
That's good.
Are Intel and AMD even considered to be competitors at this time?
Of course they are.
They are. Okay.
That's they are the only competitors in that space.
But at that time, they're competitors.
They didn't compete for AMD did not have an x86 processor in 1981.
Right.
Or 1980.
And does Intel even think of themselves as a microprocessor company in 1981?
Oh, of course. Intel
did.
was.
Okay.
Oh, yeah.
They
Intel
right.
had their
4004
their 8080 and
4004,
4004, and then the 8086 and 8088.
But this is still pre-PC.
This is post-PC.
Post-PC.
Or
Okay.
about the time that the PC had come out, which was an 8088 based
Right.
machine initially.
And that, I assume, changed everything inside of Intel. I would assume, maybe not.
Yeah, they became a PC company.
Right. So were you working at Intel when you bought the PC?
I had left Intel.
Okay.
So I had gone off on my own.
Wow.
But it was interesting. Intel had the potential to have been a PC company. The workstations that I made reference to a few moments ago were PCs. An Intel development station ran a MS-DOS-like operating system. And, all of these were influenced by RT11. And so if you were a user of a DEC RT11, you would recognize many aspects of the OS interface and the software development process on the machine. Intel was selling these at $10,000 or $15,000 a seat. They weren't interested in undercutting their existing market. But I think if they'd understood the potential for personal computing, they could have rebranded that machine and dropped it on the market. It was not that fundamentally different than an IBM PC. It was blue. Other than that, it was the same thing.
Interesting. And it was running. So what was the operating system it was running? Was it Intel authored?
It was an Intel operating system,
Okay.
but very similar to what you would have found on an RT11 system.
Right. Was the slash pointing the right direction? Was it?
I can't tell you.
I'm still trying to figure out where humanity went so wrong, and the forward slash somehow fell over and went. I guess it was CPM.
What did it used to be?
It was on Windows and DOS. It's a backslash, not a forward slash,
Okay.
to delineate path names. And on Unix, famously, it was a forward slash.
And that was, of course, a challenge in building this DOS to Unix file server, was dealing with the equivalence of forward and backward slashes. And then had to deal with a number of the of differences in semantics between the Windows the DOS environment and the Unix environment. I made a mention to the file control block on DOS that programs would do I/O after they closed the file. Well, that doesn't work on Unix. So if you have if your server program, which is serving I/Os on the Unix side, does a file close, all the context for that close is gone. But I had to implement a cache of previously open files
to accommodate
in
this.
order so that
Oh my God.
when a read came in on the old file descriptor, I would have, I'd be able to uniquely identify it was for that file descriptor and then reopen the file.
And would this be considered a bug in the? I mean, was the interface that you were allowed to do this deliberate, or
I
was
suspect it was deliberate. Some of the top-selling applications of the day, like DBase, made common use of this. They closed the file, and there were some advantages to closing the file, I assume, in cleanliness and not be able to flush buffers, but then continue to do reads and writes on the file.
So what handle do they have back to operate on that file? Do they have an FD equivalent?
It's just like an address.
Okay.
File control block.
But is that address reference? How is this safe at any speed? Is what I'm trying to wrap my mind around.
I don't think it was.
Okay.
This was a real memory system. If you wrote over the file control block, it would have random information in it. You do an I/O on it, you're changing random spots on the disk. So
and the machine would reboot, would do
course.
triple fault, or you'd just get random corruption or anything else.
And then you'd reinstall. Yes. This was not a protected memory system. One other fun bug in building the PC interface product was that it was on a DOS system. You can truncate a file by writing to. Oh, actually, I'm trying to remember this how this worked, but you would be able to write 0 bytes to an arbitrary location in the file. I think that truncated.
Okay.
And so being able to, and that's one reason people would write on a closed file. They would know that a portion of that file was unused space because they compacted it, for example, and then they would do a 0 byte write after the last byte that was in use, and that would truncate the size of the file.
And so you had to honor that.
Oh, we had to. Well, the first implementation of that on Unix was to rewrite the file and just write it up to the point where the truncate occurred, and then you just don't write. You'd close it. But of course,
now the performance is terrible.
Well, it was particularly terrible if the application you were supporting is one that was going through a compaction algorithm and wanted to be back in clean state after each phase of the compaction algorithm. Well, it may be 1,000 phases in compaction. So there'd be 1,000 of these truncates.
Oh my gosh.
And now you're copying the file over itself, basically copying to a new file and then renaming and deleting the first one and then doing it again 1,000 times on the Unix side. So some very simple, fast operations on DOS were taking days on the Unix side. So we had Bell Labs implement a truncate operation.
That's ftruncate.
Which is still there.
Yeah, ftruncate is still there.
And so ftruncate was added in order to support this behavior on DOS.
Oh my God, that's the origin story of ftruncate?
That's correct.
What is ftruncate today?
Ftruncate is the Unix interface to truncate a file, but it's explicit about it. And what Jeff is pointing out is prior to the introduction of ftruncate, there was no way to truncate a file.
Yeah,
you'd have to rewrite it. I mean, you could open it trunk, but that might not have existed. I mean, ftruncate certainly.
No, this was why it was added. It was because
that's amazing.
And AT&T was sponsoring this work.
Right.
So
on the 3B2.
On the 3B2. And so they added the truncate operation because, closing a DBase file took days.
And is this, let's see, is this system 3 or is this like 7th edition? Where are we here?
This would have been 81 or 82, maybe.
Okay.
Right in that time frame. Probably 83. I think that would have been system 3.
So we're still, sorry, Jess. We're still 5 years before Jess is born. So we're still pre-Jess, but we're definitely post me. But certainly not on Unix. So that is amazing. That is the origin story of ftruncate.
That is actually amazing. I've used that a lot.
ftruncate, yeah.
Yeah.
I can probably only lay claim to one other Unix system call. And this was for a project I did a few years later for a company called, I think it was Power Office. They were a division of ICL, which is a British computer company, International Computers Limited.
Yes.
And this was a group based in Virginia. And they called me out because they had a performance problem. And they said there was a virtual memory issue. The system was swapping. It was, overcommitting memory. So I went ahead and just, put a logic analyzer on it, which is how I used to debug things. And quickly determined that no, this was not a virtual memory issue. They were simply out of CPU instructions. But why were they out of CPU instructions was the interesting part. It was simply the cost of handling every keystroke. This was an office automation system. And when the engineers developed it, they typed at one speed, but the customers were much more talented and could type 3 or 4 times faster. So a system that was sold as a 20-user system was only supporting 7 users because these 7 users really could type. And they could hit the 50, characters, 50 words a minute, and the engineers developing it simply could not. I mean, our mere mortals, we were not able to type at those speeds. So the challenge was, well, do you optimize the trap interface or simply handle less characters? So I remember thinking about this problem and said, okay, what you really need is better line editing, because really what all you're doing is echoing a character back 90% of the time. And then when a special character is hit that goes into the control language of the word processor, or you reach the end of line, then you needed to do something a little special. But otherwise, you could have, and since they built their own terminals, you could have an intelligent terminal that could do local echo. But the only choices we had for terminal I/O were cooked or raw. So I proposed gourmet mode. And there were a few versions of Unix that were shipped for a number of years that had gourmet mode as a TTY line discipline.
I was going to say, so this is a different line discipline, and you would indicate that I'm using gourmet mode.
And you'd specify what the escape characters were. What were the characters that would cause you to move out of echo mode and back into a raw mode? And then what the condition was for going back into this local echoing mode.
But gourmet mode has been lost. Yes, I mean, do we still have gourmet mode?
I have no idea.
All right,
I hope it's been lost. I mean, you shouldn't. It doesn't necessarily benefit anyone today. I mean,
right.
These are not the ability to handle keystrokes through the trap interface is no longer a constraint on system.
No longer a limiter on or CPU performance is no longer the limiter based on the number of keystrokes we can handle. That is amazing. Yeah, I'd have to, because so much of that stuff did survive, and then of course long outlives its original intent, and then can kind of come haunt us in modern times.
Yeah, I think I saw it in System 5 Unix at one point, but I don't think it's made its way into Linux and more modern versions.
Because truthfully, ftruncate actually caused me a very painful bug where I actually, because there are multiple ways to truncate a file in Unix, otrunc being the common one, ftruncate being a lot less common, and I made a modification to the kernel, and I missed the ftruncate code path, and as a result had this really nasty bug because I had missed ftruncate. So,
well, I will indirectly apologize.
No apology required. It was my mistake for missing it, but it's just interesting at how these abstractions are added. So with gourmet mode, did you implement? I mean, did you interacted directly with the group to go implement gourmet mode, or how did you implement it?
We worked with the kernel group within ICL, and they implemented the gourmet mode handling in the TTY controller, and also in their terminals.
In their terminals. And so does ICL have their own Unix at this point?
They had their own Unix version. And they had a few pretty solid engineers who were supporting kernel development.
So they're taking AT&T code and running it, or modifying it effectively.
Yes.
Wow. Where after ICL?
Yeah, was it Veritas after that?
Well, ICL was just a 1 month assignment. I just parachuted in because they had a product problem.
Because they had just done a press release stating that they had a big problem
that they had a solution for. That was
one of the folks from Intel who I'd worked with earlier was running that group, and he had a problem, and he said, "Okay, this worked once before," so I got that contract. I was just contracting.
That's great. And then where next?
I worked with a group called Locust Computing Corporation. So Locust was based in Santa Monica, California. It was a group that had spun out of UCLA, run by Jerry Popek, who's a professor at UCLA. The Locust is a distributed Unix, and it's a great. You can read a lot about Locust today.
Really? Wow.
Yes. So the team is still around. They're not as a team today, but many of the individuals who contributed to it are still around, and they have a tremendous. It was really a groundbreaking product. So this was a fully distributed Unix. It normalized and globalized all identifiers, so process identifiers, so file handles, pipes, references to memory, actually to like memory segments across a cluster of machines.
Wow.
And then you can migrate processes between machines. You were able to build, a distributed software that behaved the same on multiple machines as it would on a single node.
When is this?
This was early 80s, so 83, 84.
Wow.
Locust was being
That is
developed.
cool.
Yeah.
And it's a great project. I think you might want to dig into this with some of the Locust team.
I definitely want to dig into it. I
Yeah.
had never heard of it.
Charlie Klein is living in the Bay Area. He's one of the early architects of this product. They did a phenomenal job. They sold it to IBM.
Okay.
And IBM did release it, but I think it was a very limited release and was really just an investigative system.
So I'm trying to think of the distributed Unices, and that is extremely early for any. I mean,
this was a definitely a groundbreaking system.
It must have been.
And it was fascinating. And the work I did with PC interface was done with Locust.
Wow.
So they had the contract with AT&T.
And this is over what network substrate? I mean, this is like so early that
This was Ethernet.
it is Ethernet. Okay.
Yeah, coax Ethernet.
Okay.
10.
But Ethernet itself is very young at this point. Right?
Very young, yes.
That is just amazing.
That is crazy because that's something that like people move processes from one computer to another still today, but like that in the 80s, that's cool.
In fact, I remember when a new developer would join the team, they generally had never seen Ethernet before. And so I would explain, okay, here's this coax cable. We have a tap on the cable, but you always need to keep a terminator at the end of the line because if you don't, the ether leaks. That was the joke that this was a pressurized cable.
Yeah, exactly.
So you need to keep it capped in order to keep that in the wire.
That's great. And meanwhile, you've got someone who's terrified of taking the cap off because the ether is going to leak all everywhere. Yeah, Steve, don't worry. Yeah, it's fine.
Okay?
Yeah, it's okay.
All right, I won't take the cap off.
I mean, actually, please don't take the cap off. But so that's just an amazing system. Because you think, I mean, it's like just you're describing like the migration we do today. We do, but we don't share a process namespace across multiple machines.
No, that's actually like super groundbreaking.
It is. Cool. I mean, it's So why was it commercialized? It sounds like it was commercialized.
Well, it was productized by IBM.
Yeah.
I don't know what level of commercial acceptance it had achieved, but it certainly advanced the science forward, and a lot of people were influenced by the work that Locust and IBM did there.
Yeah, I can imagine. Where did those folks end up? What did they end up doing afterwards? What were the next systems?
Various things.
Yeah.
But really great team, and they did some great work. And again, all of this came out of UCLA.
Out of UCLA, yeah, that's just an amazing. Because again, I'm just going through and thinking of I mean, Amoeba. I don't know if you'd call it. Amoeba was not a Unix-like system, but another transparently distributed system. But Amoeba wasn't for another almost decade, right?
No, this was
late 80s.
This was Unix.
Yeah,
So,
that's actually Unix. And so it was actually derived from AT&T Unix.
Yeah.
Wow.
That's so cool. We should get them on the podcast.
Yeah, we'll take care of that.
Yeah, exactly. I would love to get that. That would be really interesting and just interesting to capture what I'm sure they must have pioneered a bunch of abstractions in order to. That's wild. So you had an early view of what a distributed system could go do at a time when people were probably not really appreciating them.
I think that was the issue. I don't think that it was necessarily solving a problem people had at that point. Unix had far more substantive limitations that were keeping it out of commercial computing. And in the early 80s, Unix was starting to achieve success in desktop engineering workstations and in scientific computing. But it really wasn't until 1990 that we started to see widespread commercial adoption for enterprise computing, replacing the IBM HP and DEC mid-range OSs. So,
right. Yeah, I mean, I'm just thinking about all the ways in which I know Unix was immature in the early 80s, and to make that thing distributed is just that's amazing. All right, so where does this find you then in the 80s? I mean, what's
Well, interestingly, I moved to the Netherlands and had some fun. Well, after we licensed PC interface to Sun for NFS, I sort of could look forward a bit and saw a revenue stream for a number of years. I took a royalty on that product and said, if there's a time in your life to do some traveling, this might be it. I've worked with Philips Data Systems in Holland. That's actually where I met my wife, Marika.
Oh, wow.
And so we moved back together. But when I returned to the U.S., it was to restart a company that I had helped start before I left the country. And this was a firm that was originally called Tolerant Systems. And Tolerant was to be a fault-tolerant computer company. Their Tandem had made a name for itself and was achieving commercial success. And the feeling is that if you could do this at a lower cost, there'd be a market for a highly available lower cost computer. And the notion was to build shoebox machines that you would put multiples of them on a network, and then you did some replication between them, and you could assure for environments that needed lower performance but higher availability. This could, like process control systems, this could be an interesting solution. For a variety of reasons, I'd actually decided to move to Europe at that point after enjoy the fact that I knew I could be supported for a few years. Be irresponsible for at least once in my life, and the company evolved in a little bit different direction. It's hard for people not to compete against others who are in the similar space, and the dimension that we frequently compete on is performance. So it got bigger, and eventually was a multi-$100,000 per node computer system. About the time people started to discover that fault-tolerant computing really wasn't a sector. People weren't buying these machines because they needed to have true nonstop capability. What they needed was better availability and data integrity than a typical Unix system could offer. When I'm moving back to the US, I was speaking with co-founders of the company, those I'd started the company with years earlier, and they, were thinking that what they really needed was a software company that could provide higher availability and a better file system and data integrity than the Unix platform was capable of delivering in 1988. And this became Veritas software. So we first created a company called Tolerant Software that was going to be fully owned by Tolerant Systems. And about a month later, Tolerant Systems came crashing down around us. So we took over the company effectively, and we were a 5-person software company, and then started to build that up. But we didn't actually use a single line of code from the Tolerant Systems product, because what we needed was something that was a very heavily customized version of Unix. We really did need to build something that used well-defined existing interfaces. So the System 5 VFS interface for the file system, the block and character device interface for the logical volume manager, and to be able to deliver these in a format that the Unix system OEMs were capable of receiving it. And that was the genesis of Veritas software.
Wow.
Veritas software.
That's so cool.
Wow.
That's so cool.
So that it came out of this
Yes,
other
it was.
kind of failed effort. That's interesting. And was Tolerant making hardware? They were just making software.
Tolerant was a hardware company.
Okay.
Oh, wow.
When we created, we were Tolerant software for probably about 6-7 months.
Okay.
And we brought in a new CEO who had been on the board of Tolerant Systems. And we decided he needed a full-time job, and that was Mark Leslie.
Huh.
Oh,
and
wow.
Mark was a transformative CEO for us. And the first day on the job, he says, guys, Tolerant has a bad name. You can't be tolerant anymore.
We're intolerant.
So
We're going to be intolerant.
We're going to be intolerant.
Exactly. There you go.
So we held a contest to come up with a new name. We all picked a name out of the hat. And oddly, the one Mark had suggested
Weird.
won.
Well, look at this. It's the name that I put in the hat.
Exactly. But
It's a good name.
it was a great name.
I mean, it
And-
really is a good name.
And so we became Veritas software. And of course, it really did reflect on, that we were
What you're
trying to
trying to
provide
do.
a state
Yeah.
of truth. And we built a logical volume manager that supported replication, and it even eventually supported software RAID 5. But more importantly, it allowed you to grow and shrink a volume dynamically. And our file system, the Veritas file system, didn't require a structural FSCK on system restart. So you have to think back to 1989. Disks are getting bigger. So they're no longer 5 megabyte hard drives. We're now dealing with 50 and 100 megabyte hard drives. The structural FSCK that used to take 35 minutes was sometimes taking 12 hours to complete. So imagine you deployed a UNIX system in a mission critical environment, let's say the paint shop at an auto factory, and that system has a glitch. It crashes. It happens sometimes. But the recovery from that crash could take you half a day. Well, clearly it's a non-starter. You never would have deployed the Unix system in that environment because it didn't meet the availability needs of the application. Or imagine you had a system which ran out of space in one of its file systems, and now you need to add additional space. Well, how would you do that in 1989? And the answer was pretty simple. You back everything up to tape, you repartition your disks, you create a new file system, and then you recover from your backup, because the backup and restore process is error prone, and you potentially are putting your data at risk simply to change the capacity and rebalance capacity between file systems. So this was a non-starter. It was the reason why Unix had not achieved its potential in the commercial market. And as a company, Veritas was there to enable OEMs to be able to deliver their systems into environments that required high data integrity and high availability. So with VXFS, we use an intent log for all metadata changes to the file system. And on system recovery, we reapplied the intents and recovered to a clean state without having to do a structural scan.
So is this the
of the file
origin
system.
of what's commonly known as RAID now?
And this isn't RAID, but this is the first real commercial implementation of a log structured file system. I mean, I think it's
Well, it wasn't a log structured file system.
interesting.
No,
Okay.
no. In fact, it was an extent mapped file system. But the metadata, the file system control information, was logged. So the log didn't include actual changes to file contents.
It is only metadata.
It was strictly metadata.
Okay.
But it obviated the need for the structural FSCK. You could recover in seconds as opposed to hours.
Right.
And I had seen large systems that took 2 days to recover from a power failure. There were a lot of attempts that others had made to solve these problems by, let's say, having a clean bit that they would periodically set in the file system.
Right.
And then if the system crashed while the bit was still set clean, you could avoid the FSCK. The problem is that
It's never set.
It's never set.
Right,
in a
exactly.
busy system,
Right.
there's always IOs outstanding. So in fact, you were still doing your structural FSCK. So this was VXFS, the file system, and VXVM, the logical volume manager. The logical volume manager did implement RAID, but most customers used it for to be able to migrate and move storage. If you had a disk that was showing errors, you could take the used slices on that disk and simply drag them to other disks where there was free space. The storage would migrate. You would be notified when the disk was empty. You were free to replace it. Previously, those had been major disruptions on system availability.
And that's actually still a challenge for us today, is actually being able to remove a device that's in either a RAID set or a ZVOL, what have you, is a challenge. So, and this is RAID at this time is still mainly hardware. This is all, you guys were doing software RAID effectively.
Well, there really
mirroring.
wasn't much hardware doing RAID either at that point.
Oh, really?
No.
Interesting. Okay. So this is, because RAID is what? I mean, that's David Patterson in the mid 80s, right? Early 80s.
Yes. And a fellow at CMU, and blanking on his name now, that's terrible. But he had, Garth, I'll think of it in a moment, but he had written a sort of a groundbreaking paper on RAID as well. But the use of the Veritas volume manager was largely storage migration. Effectively, it's virtual memory for disk, and offers you the same basic advantage that virtual memory did on RAM. You no longer are dealing with physical extents, but they're logical extents, which then you map onto physical extents, and you're free to change the physical locations of those logical extents without impacting availability of the applications.
All right, we're going to take another quick break, and we'll be right back with Jeff Rothschild. On the Metal is brought to you by the Oxide Computer Company, where we're going to try a new feature shamelessly ripped off of Reply All's Yes, Yes, No, where our boss, Steve Tuck, brings us a tweet he does not understand, and Jess and I try to explain it to him. Steve, do you have a tweet?
I sure do.
Go for it.
The tweet in question: UEFI pre-boot network stack engaged the onboard NIC in such a way that it would write back DMA to particular physical memory pages sometime after control was passed to the bootloader. Corruption would occur somewhere in the user parts of the RAM disk. No idea.
No idea. Jess, do you understand this tweet?
So I understand definitely the part about the UEFI pre-boot networking stack, but the part about DMA is in question marks. So it's like, I guess you're not really sure where that's
You're
going.
overthinking it. I understand this tweet. Running on-prem is painful. This is dealing with an awful firmware bug. The firmware has overwritten part of the operating system in a way that is extremely painful to debug.
So who do you go to in that case?
Who do you go to?
You definitely strangle one of your vendors.
You strangle one of your vendors, and unfortunately, your vendor is a PC vendor because all of the existing computer companies are selling personal computers. What we need is a new computer company.
So this is just saying I'm in intense pain trying to run systems on premises.
That's exactly what it's saying. Steve, what can someone do if they're in intense pain running on premises?
Well, if someone is running in intense pain on premises, what they should do is go over to oxide.computer to learn a little bit more about how we are going to take that pain away.
Help is on the way. Join us at oxide.computer.
You are not alone.
All right, we're back at On the Metal with terrific tales from the hardware software interface. I feel like I could go on for days. This is good, Jeff. You're holding, you're holding us just mesmerized. Veritas. We were talking about Veritas, total groundbreaking technology, and I mean, really truly years ahead of its time. It would take a long time for any of the other folks to really catch up to Veritas.
It was pretty much the end of the decade before you started to see other logical volume managers and file systems that preserve structural integrity coming into the market.
Yeah, and I can tell you, being on the inside of one of those companies at Sun, where Sun loved Veritas until
and hated Veritas
and hated Veritas, and it's the frenemy relationship, not that uncommon, right?
It absolutely was.
And as the years went by, really wanted to we do our own, and boy, there were a bunch of attempts at it, and they were not good. And you saw, I think people really appreciated how much had been done and how hard it was to actually get all this stuff correct. And so how long are you at Veritas? When do you?
We started the software company in the end of 88, beginning of 89. I left in end of 94. So about a year after the IPO, or just after the IPO. And I left largely because the internet was happening. And I was really excited about what you could do that might be a lot of fun. I will admit that I there was a point where I didn't want to talk to people about device drivers anymore. I used to do a bit of sales at Veritas, so I wore many hats. I did some prototype engineering. I did a little engineering management. I would do product management, and I would also grab a bag and go on the road. And one day I was sitting in a meeting, and I think it was my fourth meeting that day, talking about the BDEV switch, CDEV switch, and how the how IOs were scheduled or something to that effect. And I just said to myself, tomorrow I'm doing something different. I left in order to start something that would be fun. And the fun thing I thought about was online multiplayer games. And started a company to do online multiplayer gaming because it seemed like the most fun thing you could do with the internet.
In 1994?
1995 at that point.
Okay.
Yes.
Yeah.
Wow.
That's early.
That's early.
Well, it was early. And that actually, you could put that on the as the epitaph for the company.
It was early.
We were too early. We were doing this with people had 1440 baud, dial-up modems.
Yep.
The latencies were very high, and we put a lot of energy into dealing with latency. We had matchmakers that would very carefully look at the latency of individual players and group people into game sessions based on their proximity in space to each other. That is in network space, not physical space, though there's a relationship. And we worked with some early internet service providers and co-locating equipment, which was an interesting exercise because the first time we approached a internet service provider about co-locating our game servers in their network, the head of operations for this company said, "Over my dead body, will any customer ever put a machine in my data center?"
Wow.
And of course,
that's putting it out there.
In 5 years, that was their business.
Right.
But it was an interesting response. And we finally found one provider who, when we asked the question, said, I don't know why you want to do this, but I've sort of taught myself that if somebody asks me for something, listen and we'll work with you. And that was PSINet. And so PSINet worked with us to create optimized traffic. So we were able to prioritize the game traffic on their network, and we located game servers throughout their network, geographically dispersed, in order to manage for latency, because this latency mattered.
Right.
We also did a lot of work in the client to game server link that would be irrelevant today. We were squeezing 2-3 bytes at a time out of the game protocol. And today that would be irrelevant. We were working with the game developers on algorithms they could employ to hide latency. So when you fire a weapon, make sure there's a big explosion and a lot of smoke, because that gives you time to resolve state between all the clients so that when the smoke clears, everybody sees the same player is dead. When in a first-person shooter game, you would be sure that if you were shot or you shot someone, one hit wasn't a kill, because a single hit required precision in how you adjudicate and distribute state. But if it takes multiple hits, then there's time to figure it out. And the lack of precision in the network and in your protocol was hidden by a lack of precision in the game experience itself.
That's great.
And so we worked with the developers on helping them build multiplayer gaming. We actually had one of our fellows spent a month in Mesquite, Texas with id Software, converting Quake from IPX, SPX to IP. So it was originally written for the Novell network protocol, LAN protocol. And so we converted that to be internet-capable game, and
so you could play Quake over the internet.
The first version of Quake had an M-Player splash screen on it, giving us credit for that work.
Wow. But it was, you said the company itself was too early?
We were too early. Yeah, we were too early. And so eventually it sort of divided up and assets were sold to different companies. It did go public, but that was 1999. And just like there was an era in baseball where everybody's record has an asterisk on it. I think a lot of companies should have asterisks on their 1999.
I've been 1999.
Exactly. The 99 IPOs, I don't think, deserve the same credit as before and after.
It was a very different era, that's for sure. So what was next for you after that?
I did a few projects just as a consultant to the projects. I helped with Walmart.com and a company which did a storage controller that was eventually purchased by Brocade called Rhapsody Networks. And was
the storage controller. So you're back in the device driver.
Oh, of course.
Can't stay away.
I should have erased all that from my from my resume so people would forget, but it kept coming back to haunt me. So I couldn't get out of that industry. Let's see, early 1995, or 2005 rather, I got a call from folks at Excel Partners asking if I could help out with a couple of company they'd invested in, a few guys from Harvard who'd started a social network. And my first response is, social network? Have you ever looked at Friendster? and they said, no, this is different. There's nothing to do with that. And so I figured I'd hang out at their office for a few weeks and help out with recruiting. And spent 10 years there.
That's cool.
And so what was your kind of first impression walking into Facebook?
Small team. I love small teams. I love people doing things from the seat of the pants, and not having a lot of process, not having a lot of rules. And there were no rules. I mean, this was a development team. We're sitting around a small table today. Well, that was pretty much the environment. Somebody was going to edit a file. They'd say, "Okay, I'm in home.php," and nobody would touch it until they said they closed it. So no source code control, no auditing. But that's small teams. I mean, I've done the same thing, 100 times. You start the project with 1-2 developers, and then you sort of have to introduce layers of process and eventually release management and testing and frameworks and the rest. But early days, you have a blank slate to start with. But it was a lot of fun. I mean, what impressed me about Facebook, because I really wasn't intending to work there. I was really going to help recruit a VP of engineering and someone to run operations, and I was bringing a few people in. The chemistry wasn't clicking. They were great folks who've really gone on to do fantastic things. But I couldn't sit in the office and watch people work and then not say, let me show you a different way to do that. And so I would sort of dive in on a few of the engineering issues. And I'd say, and at the same time, I was looking at the inbox. I wanted to understand, what are the problems this site has? What type of issues are the users running into? So I read the unread mailbox, and there were 75,000 unread messages because the person who was assigned to read that only worked weekends. She was a student and, worked weekends and read some messages and responded to them. And of course, the rate of arrival was much greater than that, she would ever be able to meet. And people were writing love letters. I mean, they were writing poems. People were saying, I showed up at school and I was so afraid I wouldn't know anyone. And using your site, I've met so many people and I feel like they're all my best friends now.
Isn't that amazing?
That's so nice.
And then,
it's a different era of social networking.
And then somebody would write a note saying, well, I showed up at college and I was so sad at missing my friends from high school, but I now know what they're doing. And they post things on a daily basis. And I understand what they're up to. And I feel so close. I still feel so close to them.
That's so good.
And I read this and I thought about it and said, Veritas, sort of a big company. I mean, 6,000 employees, $1.5 billion in revenue, thousands of customers. But I never saw a love letter from a system administrator saying, your volume manager made me happier.
Right.
I used to be afraid of losing my data until I met you.
Right. I've never seen FS Check run so quickly.
Yes. And I thought about it a little more and said, well, companies spend hundreds of millions of dollars a year trying to convince people that their products make them happier. And here is a company that spent nothing, that simply built a product, and their users are saying, I use you because it makes me happier. I thought about Coca-Cola and Pepsi. I mean, look at their ad campaigns. It's all about how their flavored water their sugar water is going to make your life better. And here was a product where people were saying, in concrete terms, their life was better because they were more connected to their friends. And the truth is, that is what matters. I mean, what really matters in your life, it's the connection you have with people. It's not the number of friends you have. It's how close you are to them. How much if you have a friend and you never talk to them, then they're not adding to your life. You're not adding to theirs. And what Facebook was doing was increasing that information flow between people, and that enhanced those relationships, and in turn created happiness for folks. And I wanted to be part of that.
That's great.
Yeah, no, that's huge.
So saw obviously the power in that, and that's in 2005.
That's 2005.
And so at that point, because I first met you in 2007, and when you were pretty well, I mean, you were pretty well entrenched in Facebook. You guys were, at that point, Facebook was really catching on, and lots of people were. It didn't feel. It felt like it was exploding in all the right ways.
It was.
And of course, I remember meeting you very viscerally, because I was talking to you when my wife was about to have our second kid. And I was going to come down and meet you, I think the day before she was due. And you gave me a warning based on your, was it second kid or third kid?
Our second was born very quickly. Yes. We showed up. My wife woke me up at, I think, 6:30. And we were on the way to the hospital at 6:45. We got there at 7, and we were really ready to go home at 7:45. So,
which, I mean, that is, Steve, you've got 3 kids. I mean, that's
record time.
That is terrifyingly fast. So I was definitely like, wow, I know this is on the medal, not on the pregnancy, but wow, that was a scary, that woke me up. I think I postponed the meeting, I think.
Because I think you were telling me that, the due date's tomorrow.
Oh, I was very blasé about it.
Yeah, and you were, 2 hours away.
Oh, I had plenty of time. And you're like, well, hold on, youngster.
Teach you a few things.
Let me slow your roll a little. Yeah, no, it definitely, but it was a lot of fun to get down there with you and the team. And so then how long were you, at Facebook, you quickly got to some of the same deep technical problems that back in the device drivers, but you got back to the metal.
Of course we did. In fact, one of the first really interesting problems that we dealt with was our use of Memcache. And for those of you who don't know, Memcache is a distributed hash table. And it has an operation called a multi-get, where with a multi-get, you take a collection of keys, and the driver then will, understanding the hash function, will sort those keys across a collection of servers and then make a request to the servers in the pool to respond with the corresponding data values. Well, we worked really hard on the Memcache code. We had to improve its scalability. We had to improve its performance. We made it multi-threaded. And in doing all of this work, we actually made it faster. So we reduced the total instruction path of Memcache down to a minimum, which meant that its variability was less as well. That is, request to request variability was less because the total time required for a request was less. What this meant was if you made a request to a Memcache pool, let's say a pool of 200 machines, and you were doing a large multi-get that had maybe 1,000 keys, you're probably hitting most of those 200 machines. So inside of microseconds, you would have 200 machines firing back their responses to your client, which is in fact a web server, but the client, your client is making this request, it gets all the responses back, and they all meet for the first time at the top of rack switch on top of your web server. And of course, the next step is buffer overflow. So you drop some packets and then you make the next request, and you're using TCP. So TCP, has variable retries, and the retries keep getting longer, and soon these requests are taking milliseconds to perform because of the retry logic, because even on the second round, you started getting buffer overflow as well. So this was a very challenging problem. It took a long time to really understand. And after that, a fellow named Mark Kwiatkowski implemented just a fantastic solution. It was a sort of a UDP version of congestion control. If you made a broad request and you dropped data, then you would make fewer numbers of, you request from fewer servers the next time. And it was adaptive. So if you got a response back from those servers and nothing was dropped, then it would try to go to a larger number of servers. And so it would break it into a multi-phase request, and it would adapt to the quality of the network and the size of the buffers relative to the size of network speed.
And all UDP, so implementing the congestion.
Everything done in UDP.
Congestion control itself, so not falling to any of, because TCP was really designed to protect the network, and you don't want to protect the network. You want to get the best latency for the most users, right?
That's correct.
Interesting. And so how long did it take to get to fully understand what was happening there?
Too long. So I'd say the better part of a year before we really tracked it down. Initially, the first suspicions were it was problems in the network, issues with switches, problems with libraries, but eventually we understood that this was simply because we were making the Memcache code faster, and if you have less variability in a faster code path. If you're talking about a half a millisecond code path, then it's going to be plus or minus 50 milliseconds. But if it's 50 microsecond code path, you're 50 nanoseconds. So
interesting. So by making it more deterministic, you were increasing the odds of actual buffer overflow at the top of a rack.
That is exactly correct. And so it took us a bit to understand why the problem was getting worse over time, because we were getting better.
You'd improve the performance, and the performance would degrade enormously.
Yes.
That must have been frustrating.
Yeah.
Wow.
Interesting. So that was probably one of the first hard problems we had. We had other issues. I mean, we had one that I'm talking a little out of school here, but we had one where the release code for configuration management missed installing mod PHP on a server, and so the PHP code was simply delivered. I mean, you ship it.
Oh God.
Yeah. So that was pretty ugly. That happened once. And I think there's still fragments of that code, floating around the net.
Yeah. That's hard to scrub the internet of all that one.
And so that just sort of reinforces, the importance of getting configuration management right and making sure that it's verified.
Well, that's funny to think that like for a misconfiguration, we accidentally shipped the source code. That's like a new kind of failure mode at that time, right? That's not something we think of in a non-networked system, certainly.
Well, and it sort of elevates the importance of configuration management. I mean, people sometimes think that these are, sort of like the basic problems. They're not the exciting problems, but in fact, if you don't get them right, you can't do anything.
What was the? I mean, I have to imagine the single instruction found back at Intel was maybe up there, but was there one that was the most gratifying kind of bug you found or resolved in your career?
I would say that if I had to point to, the one that we spent the most time on, I'd say the problem I just mentioned. Trying to understand why it is the better we made Memcache that in some ways the worse it performed. We could increase the total number of requests per second that a server could deliver, but these error rates continued to increase. And I think that took longer than it should to shake
also,
out.
you're a long way from being able to just use a logic analyzer to figure it out.
Yeah.
I mean, it's a big, complicated system.
Yeah, and we had to understand the switches and get the right metrics out of the switches to understand what was happening.
That must have been frustrating, I assume.
Yeah, that was a big one. That was a big one.
To actually figure out what was going. So then, when was the genesis of the Open Compute project then at Facebook? Was that a couple years?
Oh, that was
later?
Many years later.
Okay,
so, many years. In internet time.
Right.
2 years later.
Right.
Nice.
3 years later, and the Open Compute project. Jonathan Heiliger was one of the drivers of that project, and there, of course, we're already at a scale where it simply made sense to have hardware that was optimized to task. And of course, in the early days, you're buying things off the shelf because your scale doesn't warrant doing anything else.
Interesting. So, I think that in kind of the modern era, we think of the hardware as not being important anymore, but it's still the underpinning of everything. And what do you see kind of going forward? I mean, first of all, do you throw up in your mouth a little bit when you see like serverless and cloudless and all this other kind of nonsense?
Serverless, I'm still grappling with.
Nice. That makes two of us. Three.
So I'm sure there's a rationale there, and I'm sure it's just my inability to understand it. So
don't be so sure.
No.
You got a kindred spirit in Jess.
Yeah.
So no, I'm still trying to work that one through. Yeah, but things tend to come. Everything tends to repeat itself. So ideas which you saw 30, 40 years ago suddenly become new again, and today we're looking at what do we do with non-volatile RAM. So Intel's Optane technology, as an example. There'll be interesting applications for that. And I think back to an early system I used called Multics. This was at the GE Computing Group, which became Honeywell. They were participants in the Multics project with Bell Labs and MIT. And this was a system that supported a single level virtual store. Well, so there were no opens and closes, reads and writes. You simply attached to a memory segment and you used it. And then you detached from the memory segment and it was stable. And so you wrote I/O-less software. We're actually at a point today where we can do that. And that really changes the application paradigm. The state of the application could be in the app itself. You're not having to think about storage management. But also you avoid sort of the semantic gap between read and write and what you're really trying to do with the storage. So blocking and unblocking and marshaling of data, putting it in serialized formats, all of these things suddenly aren't important to the app anymore. The data lives in the application view of the data structure and never in the storage view of the data structure. And I think that's going to offer some, for the right applications, that can be groundbreaking.
Yeah, that'll be interesting because allows for that abstraction to obviously be shifted. You still are going to have to think about the non-volatility of that state, though, right? I mean, if you leave yourself in an inconsistent state,
you obviously have to have paradigms for managing consistency and for logging and changes. So not all of the overhead of a traditional database, for example, goes away, but you're going to implement this very differently. And one of the ways I like to think about databases is saying, how well do they use their memory? A database that really makes effective use of its memory is probably performant. And one where the working set of the application is distributed across a large number of blocks, where there's maybe other used data in the block, so you don't view it as internal fragmentation, but the other data in the block may not be part of the working set, but because of the way you needed to structure your index, it was inevitable that you had this on-disk organization. Well, that database may not be as effective as it could be because they're limited by the size of RAM. And if your RAM is allocated to data that doesn't matter, then you're not going to get all that you potentially could out of the hardware architecture. So, or out of your overall spend on infrastructure. So thinking about new models for the database where it's all record oriented, you never have this notion of blocking because blocking doesn't matter in this type of a single level virtual store. I think there's going to be a lot of opportunities there.
Yeah, interesting. And it'll be the databases themselves that implement it. So it's not that everyone's going to need to think about that non-volatile consistency, but it's that we'll be able to.
Or maybe new databases. Think about it. This might be enough of a paradigm shift that it says that new databases will take advantage of this change in order to enter the market.
Interesting.
It may be some of the old ones are able to adapt to this model, but that's a future I don't think I can predict. But I just feel that this is disruptive.
Interesting, and certainly it feels like something that we're ripe for in terms of the non-volatility of main memory, or getting main memory speeds with non-volatility. Feels like it would shake things up quite a bit.
There's the potential. This is sort of like flash disk shook up the storage market. There are these technologies that are highly disruptive, and they create the opportunities for new players in the market. So I think this is one as well.
So given the number of trends that you've been early on, let me know when you're going to the store to buy the Optane. Maybe it's now. I feel like we got to be following Jeff wherever he goes. I mean, you've
been
database
companies falling out of that.
Exactly.
Well, like everything else, unless you're wrong some reasonable percentage of the time, you're probably too slow. So I don't know if that's a good investment strategy. I'm wrong too.
Okay, well that's a relief.
I'm wrong enough to have confidence that I'm not moving too slow.
Okay, well, because it feels like you've been right a bunch of times, and you certainly have been at the epicenter of some of the biggest shifts we've seen in computing, and right on the metal all of those times. So, Jeff, thank you very, very much.
Yeah, this was terrific.
Yes, thank you. This has been amazing.
This was amazing. And
I learned an important lesson is make sure you limit engineers to no more than 3 sales meetings a day.
I think you drew the wrong lesson from that. No. Exactly. But Jeff, thank you very much. And if people want to, in terms of learning more about you or your career or some of the technologies you're interested in, is there a particular place they should go to? Or are you?
Well, there would be if I'd put something like that together, but I have to admit I have not.
Oh, okay. Well, so maybe go check out Locust. It sounds like for sure.
Maybe I need to make that as a resolution this year to document some of what I've done. But
well, if we can help you document it, we'd love to, because I think that there's just a lot in here. Well, thank you very much for your time today.
Well, thank you very much for having me.
All right, and thank you, dear listener, for joining us for what was a terrific episode of On the Metal. I am Bryan Cantrill, and with me again it's Jess and Steve. Adios. Thank you.
Bye.
You've been listening to On the Metal, Tales from the Hardware Software Interface. For show notes, to learn more about our guests, or to sign up for our mailing list, visit us at onthemetal.fm. On the Metal is a production of Oxide Computer Company and is recorded in the Oxide Garage in Oakland, California. To learn more about Oxide, visit us at oxide.computer. On the Metal is hosted by me, Bryan Cantrill, along with Jess Frazelle, and we are frequently joined by our boss, Steve Tuck. Our original and awesome theme music is by JJ Wiesler at Pollen Music Group. You can learn more about JJ and Pollen at pollenmusicgroup.com. We are edited and produced by Chris Hill and his crew at HumblePod. From Jess, from Steve, from me, and from all of us at Oxide Computer Company, thanks for listening to On the Metal.